insert any net?
No, it's on this side.
Okay.
Okay. So, good morning, and let me begin by thanking Professor Verma and Professor Gupta for giving me an opportunity to give this set of 6 lectures on classical mechanics. Strictly speaking, this topic is not part of statistical physics, but they felt it would be a good background course for this entire refresher course. I am sure all of you have studied classical mechanics at some level, maybe more than once. My presentation will be in the traditional old-fashioned way, not the more modern treatments which use relatively advanced mathematical ideas and notations. Professor Verma and Gupta felt even this will be useful, so I hope so. And so, with no more apologies, let me proceed to my lectures. All of you have been given copies of this quite well known textbook on classical mechanics by Goldstein. The most recent edition is with 2 other co-authors, I think. I would like to suggest to you, if some of you do not have the books of Sommerfeld on mechanics and Landau and Lifshitz on mechanics, they are all available in Indian reprints at very reasonable costs, and of course, they have been reprinted in Kolkata. Levant Books, I do not know where it is located, somewhere near College Street, I suppose. It is wonderful that they have reprinted the entire Sommerfeld series, lectures on theoretical physics, in an Indian edition, and I think Landau and Lifshitz's book on mechanics is also available. So, if you already have these books, very good, you are lucky. If you do not, I would, and you are interested in teaching this subject really well, please do invest in getting these 2 books in addition to Goldstein. Goldstein is more comprehensive, but these 2 are classics of the physics literature of the last century, so you should have them. My introductory comments will be descriptive. I will not write too much on the board because this is familiar material, and then at a certain point I will start writing things on the board. Well, we all agree that classical mechanics is the oldest branch of physics. It is the basis for all other areas of physics. It has a very rich formal structure, which was developed in gradual stages over more than a 100-year period after Newton. So, it is good to learn traditional classical mechanics in some detail, because it serves as a basis, a pattern for later learning electromagnetic theory, statistical mechanics, as in this course, special relativity, general relativity, and as a starting point for the transition to quantum mechanics. So, what I will be describing in these lectures will be largely a mathematical development, but based on the ideas of physics first stated or enunciated by Galileo and Newton. So, to begin with, everything will be based on the Galilean Newtonian principles of physics, and then as we go along, we will add ideas of symmetry, group structure, and so on. The development of new mathematical methods to express physical ideas goes on all the time. It happened throughout the 18th century after Newton at the hands of Euler and Lagrange and so on. They elaborated what Galileo and Newton had said, and in the process a lot of very high quality mathematics was developed. In fact, for you can say 150-200 years, physics and mathematics developed hand in hand. Many new ideas in mathematics came because of the needs of physics. Okay. Now, the foundations of classical mechanics, they were summarized and they were stated by Newton in his great work, the Principia. And this work was based on his own discoveries as well as the work of his famous precursors. You know many of their names. Newton made very specific assumptions about the nature of space and the nature of time. He said that each of them was absolute, and also he made assumptions that space obeys the laws of Euclidean geometry. So, Newton has given specific form to his 3 laws of motion. I will quote from the book by Sommerfeld, and I will not write them down because you are all familiar with it, but it is nice to see in what language Sommerfeld stated them. So, the 3 laws of Newton in Sommerfeld's language is as follows. The first law: every material body remains in its state of rest or of uniform rectilinear motion unless compelled by forces acting on it to change its state. So, this was a very great discovery actually. There is a beautiful recorded interview with Richard Feynman called The Pleasure of Finding Things Out. It is available on YouTube. It is available in printed form also, and he describes what a wonderful result, law of nature this was that Galileo had discovered, and how Feynman learnt about it for the first time from his father when he was a young student. So, this is the first law. The second law in Sommerfeld's language: the change in motion is proportional to the force acting and takes place in the direction of the straight line along which the force acts. So, this is the F equal to ma second law. The third law: action always equals reaction. The forces that 2 bodies exert on each other are always equal and opposite in direction. So, these are the 3 laws in the Sommerfeld description. I might just mention that in the book of Landau and Lifshitz, these 3 laws are not given in one place in a combined way. They are sort of scattered at different places in the text. Okay. Now, from the physical point of view, we have to understand these laws are valid in a special class of reference frames which are called inertial frames, and this is a very important concept. So, a few words on the physical content of this idea. For experiments which are local in nature involving limited length scales, a laboratory fixed on the surface of the earth is a good approximation to an inertial frame, but it is not truly inertial. And let me explain why it is not truly inertial. There are 3 effects you can see which make it not quite inertial. The first is the rotation of the earth on its own axis. Suppose you were to remove that non-inertiality. Imagine a reference frame not rotating with the earth, but fixed in relation to the sun, but located on the earth. That is, you subtract away the earth's rotation. That is a little better definition of an inertial frame, but it is still not very precisely inertial because the earth is moving around the sun. So, that causes some amount of non-inertiality. You subtract that. I will give you numbers in a moment to give you an idea of the magnitudes. So, then you say if you compensate for the revolution of the earth around the sun, you get a better approximation to an inertial frame. Then you go one step further. The sun itself is moving in the Milky Way. Suppose you subtract that. Is it even better? Well, yes, it is. And let me now write for the first time some equations so that you get an idea. I want to emphasize how important this idea of an inertial frame is. Of course, later physics has shown it's an approximate idea. With the general theory of relativity, even that has its limits. But for our purpose, for classical mechanics, we must get this idea clearly in our minds. I will use the acceleration due to the earth on bodies near the surface of the earth, little g, 9.8 meters per second squared, and express these 3 non-inertial causes, non-inertiality in terms of this. I will not write all the words, I will just write expressions. First, I will give you an idea. Because of the rotation of the earth on its own axis, a laboratory fixed to the surface of the earth is non-inertial. To what extent is this non-inertial? Well, it's a circular motion, the rotation around its own axis. And so then I will just write here Earth's rotation about its own axis leads to such a frame being non-inertial to this degree, roughly 1/300th of little g. So, if you imagine a laboratory fixed in space with respect to the center of the earth, but not rotating along with the earth, this is the correction that is involved. Then you go to the next correction, the earth revolution around the sun. That also causes the frame to be non-inertial. To what extent does this spoil the inertiality? It is 1 order of magnitude less roughly. Okay. Then the third one I mentioned is sun's motion in the Milky Way. That's also a rotational motion. Each of these are centrifugal acceleration, v squared over r. And if you have not done this kind of calculation, it's something for you to familiarize yourself with. Calculate for yourself each of these in terms of little g and make sure you get these results. To what extent does the sun's motion around the center of the galaxy make things non-inertial? It's much, much smaller. Okay. So, here I quote from Einstein, very beautiful quotation, and most physics students are not aware of the way in which he expressed it. He says, "We may look upon the principle of inertia as established to a high degree of approximation for the space of our planetary system, provided that we neglect the perturbations due to the sun and planets." So, what you have to understand is that from the solar system point of view, roughly, that is where Galileo's and Newton's work was based, you can say. An inertial frame in which Galileo's laws are valid is one which is not rotating with the earth, not moving around the sun with the motion of the earth, not rotating with respect to the center of the Milky Way along with the sun. Remove all those things and then imagine a reference frame fixed with respect to the stars in the sky. This is, so I will leave it at that, and that is what Einstein meant by this statement. Now, I also mentioned that Newton's laws were written by him based on the work of his predecessors and then his own contributions. And this is very important to know, that the whole science of mechanics developed gradually. Many, many people contributed to it. There is a beautiful article by Professor Amitabh Ghosh of Shivpur Engineering College. He is there now. He used to be at IIT Kanpur long ago. Then he was IIT Kharagpur director, and now he's at it is now a central university. Bengal University of Science and Technology, deemed university. So, he has written an article in Resonance, volume 14 in 2009. Resonance, volume 14, page 1153, 2009. A very nice pedagogical article by Professor Amitabh Ghosh on the origins of classical mechanics. Okay. It tells you what were the ideas already thought about before Newton came and what did he put together. Uniform acceleration was an idea which was studied at Oxford and Paris in the 14th century, that is 1300 and something. It culminated in Galileo's work and the experiments he did with the leaning tower over the 16th and 17th centuries. Okay. Late 1500s, early 1600s. The first law stated by Newton was found by Galileo, which you will see very well described in that Feynman interview I mentioned earlier. It was known to Descartes and had been stated by him. All this is very nicely described in this Amitabh Ghosh's article. Kepler had an idea of concept of the force. He thought of it as a way in which the sun acts on the planets and makes them move, but he thought force was proportional to speed. Okay. That is where Galileo's work was crucial. The idea of momentum was known to Descartes, and the second law was found by Huygens. It was quite surprising. All these people contributed bits and pieces of the overall picture. The third law of motion, equality of action and reaction, is entirely due to Newton. But Newton's overall contribution, the magnificence of it, is putting it all together as a logical, as a axiomatic system. Newton's third law made it possible to make the transition from describing the motion of a single body or a single point mass to systems of mass points, rigid bodies and so on. It was only with the third law that all this was able to be accomplished. And as you probably know, Newton's third law also led to the law of conservation of momentum. Okay. So, most of the formal developments in classical mechanics during the 18th and 19th centuries have been in the context of what we today call non-relativistic mechanics or Galilean relativity, prior to special theory of relativity. You must keep this in mind when we go through some mathematical derivations very soon. Against this background of non-relativistic mechanics, we will describe the transition from Newtonian description of motion to the Lagrangian description. Then we will see how to go from the Lagrangian to the Hamiltonian description, and I will also tell you a little bit about the Hamilton-Jacobi form. That is something that is not very often taught or very clearly explained. So, I will look at each of these in sequence. You have done all these things in the past, but let us go through it systematically. So, I will begin with, just take a moment off. I will begin with writing down for you something which is very familiar to you, the Newtonian equations of motion for a system of particles moving around in three-dimensional space. So, since these are so familiar, I won't explain the notation in too much detail. We have a system of n particles, point masses. All it means is that with respect to the context we are given, the motions we are describing, we can neglect the sizes of these particles. That is a physical idea. When you talk about deriving Kepler's laws of planetary motion from Newton's law of gravitation, for example, you idealize the Earth to a point running around the sun. So this is always in one's mind, that with respect to the length scales of importance in the problem, we are allowed to neglect the sizes of the bodies that we are describing. So we have n point masses with masses m1, m2 up to mn. They are moving around in three-dimensional space, and their motion is being described in an inertial frame, and I have given you the physical background for the idea of an inertial frame. So to begin with, we describe their motion using Cartesian three-dimensional position vectors in the inertial frame for each of these bodies, and each of them is thought of as a function of time. So all of these variables, three-dimensional vectors, one for each particle, all taken together, describe or define the configuration of our system of particles at a given time. That's the idea of configuration, how they are arranged in physical three-dimensional space. And so we say that the number of degrees of freedom is 3 times capital N, 3 for each of the particles. Then the Newtonian equations of motion, so we will use these abbreviations, EOM for equation of motion, later COM for constant of motion, and so on. The Newtonian equations of motion, as you all know, are for the particle number j, the mass of that particle times its acceleration is given to be, this is Newton's second law, total force on particle number j. So j goes from 1 to n. So this is written as a three-dimensional vector, capital F for force, and j is the particle number. And so this we have to imagine as being made up of two parts. One are internal forces, that is forces on particle number j due to other particles in this collection, plus any external forces due to other sources which are not included in this n-body system. So there are physical point of view is a clear-cut distinction, separation of the total force on particle number j into an internal part coming from within the system, external from outside. So if one knows the functional forms of these fj in terms of the positions, instantaneous positions and instantaneous velocities, then this is a system of ordinary differential equations, exactly 3n in number, 1 for each degree of freedom. And if for given initial conditions, which will mean initial positions and initial velocities, if these equations can be solved, then you can predict the positions x of t for all later times in terms of the initial values. Now this is just to set the background for the equations of motion in the Newtonian form. Now I go on to the Lagrangian form. So let me write here first the sequence of mathematical generalizations, extensions we go through. we start with the Newtonian form for the equations of motion, conventionally described using Cartesian variables for every position vector. Then next we are going to look at the Lagrangian way of describing this same set of equations of motion. Then later we will see how to describe it in the Hamiltonian form, and finally we will see how to describe the motion by the method of Hamilton-Jacobi theory. So let me just say that this form was essentially conceived of by Newton sometime in the 1600 and something. He wrote it all down, not in this notation, but in actually a very cumbersome notation around 1685 or 1687 in the Principia, but he had discovered it a bit earlier. The Lagrangian form was created sometime in the second half of the 1700s, roughly. The Hamiltonian form was invented by Hamilton around 1835. The Hamilton-Jacobi form came a few years after. So I want you to appreciate that. I would like to put it this way: the physical ideas, the physical principles which are the foundation for the Newtonian description of motion come from Galileo and Newton in the early 1600s to mid 1600s, you can say. And then these three mathematical elaborations or improvements are mainly of a mathematical nature. The physical ideas remained always what Galileo and Newton had written down. Okay. So at the risk of saying things I need not say, we must always remember, where did the physical ideas come from? What part of the subject is a different mathematical way of expressing the same physical idea? This, I think, is very important for you to appreciate, and I think it will help you improve the quality of your teaching if you keep this in mind. So at the possible risk of oversimplification, I would say neither Lagrange nor Hamilton added any new deep physical insight to what had already been expressed in Newton's time. I said that Newton's notation was not a good one. There is something called, he is one of the two discoverers of the differential calculus. But he used a notation, he called it by the name method of fluxions. Leibniz independently discovered calculus, and it turned out that Leibniz's notation was mathematically far superior to what Newton had introduced. I will not go into details, but if you think a little bit about it, you will see that the idea of a partial derivative, if something physically important depends on more than one variable, and you want to be able to differentiate it with respect to each of its independent arguments, Newton's notations are not very convenient. You have to use what Leibniz had given. So that is very important to know. So as I say, the transition from the Newtonian to the Lagrangian is largely a mathematical elaboration, and we will go through it very quickly. This transition from the Lagrangian to the Hamiltonian, here the basic idea of phase space was introduced, and as I said, this was 1835 or so. That also is a restatement in a new mathematical language of the original physical ideas of Galileo and Newton. I want to keep stressing this because you must know what part of the subject has its origins in facts about nature, what parts of it have to do with how we describe it. Okay, this is very important. In the case of electricity and magnetism, it is much more familiar to you. The laws of Coulomb and Ampere and whoever else, Gauss and so on, they were experimental discoveries about electric and magnetic phenomena, which were then put together in a mathematical system by Maxwell. So that was many years later. So in that way, I want you to appreciate the structure of the subject. The Hamiltonian form, as I said, it was discovered, it was invented or discovered around 1835 or so. A few years later, Jacobi gave a set of lectures on mechanics in which he took Hamilton's ideas and pushed them much further. Interestingly, the lectures given by Jacobi were written down by Klebsch, I think, of Klebsch-Gordon fame. They were written in German, and an English translation exists, made by Professor Bala Gangadharan, who used to be in the TIFR mathematics faculty sometime in the 80s or so, and it is available in printed book form, published by Hindustan Book Agency in Delhi. Jacobi's lectures on mechanics, given in 1847, is available in an Indian reprint. Okay? I tell you these things because otherwise you may not come to know about them. Okay? So the importance of, so you see that, again, we'll go into details in a moment. The Newtonian description was based on properties of physical space which he assumed, and we can say it was a description using Cartesian descriptions for positions of particles. The Lagrangian method gives you more flexibility, allows you to describe the idea of configuration in more convenient forms. I'll come to it in a few minutes. The Hamiltonian description brings in the idea of phase space, and some mathematicians who have been very good, who are very good friends of mine, have told me they appreciate the mathematics much better. This was one of Hamilton's greatest discoveries, the idea of phase space. At that time, it might have seemed a luxury, not essential for physics. But then it turned out, after the Hamiltonian form of classical mechanics was developed, it became the language in which classical perturbation theory for the description of astronomical phenomena was all worked out. And that was in the latter half of the 19th century. Even statistical physics uses the ideas of phase space in a very important way. And then in 1920s, 25, 26, 27, it turned out that the Hamiltonian version of classical mechanics became the starting point for the creation of quantum mechanics. Heisenberg's work on matrix mechanics was based on Hamilton's equations. Schrodinger's wave equation was based on the Hamiltonian function. And Dirac's work was based on deep, important properties of phase space, which had been created by Hamilton. So it's such a rich subject, it is good for you to once in a while sit back, take your eyes off from the equations, and understand the sequence of and dependence of ideas. The value of Hamilton's work was therefore discovered 90 years later, when quantum mechanics was developed. Okay? So keep this in mind. The Hamilton-Jacobi equation, which is a very beautiful development in classical mechanics, not often taught, turns out to have been the starting point or inspiration, you can say, for the Schrodinger wave equation. So each of these developments in classical mechanics has played an important role in the discovery of quantum mechanics. And I am tempted to add to this. So the initial discovery of quantum mechanics in all its forms, matrix form, wave form, etc., was based on the Hamiltonian description of classical mechanics. A few years later, Dirac asked the question, is there any role for the Lagrangian in quantum mechanics? It's a beautiful question to ask. And this is something he did in 1934. And he tried to bring out the importance of the Lagrangian from the point of view of quantum mechanics. And he took his discussion up to a certain point and pointed out and showed deep analogies between the Lagrangian version of classical mechanics and quantum mechanics as it was then known, 1934. A few years later, 1939, Feynman started working on related problems. And he was a student. I will take a little time to tell these historical stories. He was a student of John Wheeler at Princeton University, and he says that he was thinking about related problems, but he was not aware of Dirac's 1934 work. And there was a physicist from the continent visiting Princeton at that time, Herbert Yale, J-E-H-L-E. It's a name of those days. And in discussions, conversations with Yale, Yale told Feynman, there is a paper of Dirac you should have a look at, 1934 paper. That is how Feynman came to know of Dirac's work, and then he took it, you can say, to dizzying heights. He found a third way of describing, of setting up quantum mechanics called the path integral formulation of quantum mechanics. Okay. So I think it's a nice illustration of the fact that sometimes new mathematical ways of describing given physical laws may become very important and valuable very much later in time. You never know when it's going to be important. So the Lagrangian also leads to a version of quantum mechanics. So I can now put it in this way. These three mathematically mathematically new ways of describing Newtonian physical principles give you three forms of classical mechanics, each leading to a version of or a description of quantum mechanics. This goes to the path integral form, completed by Feynman in 1942 when he wrote his PhD thesis. That thesis is available in book form, published by World Scientific. It's a very nice thing. It's less than 100 pages, but it's a beautiful document. The Hamiltonian form leads to the Heisenberg matrix mechanics version of quantum mechanics. The Hamilton-Jacobi form leads to the Schrödinger wave equation formulation of quantum mechanics. So keep all these things in mind. I think it will make you feel it's worth spending little effort in understanding all the relationships and developments at the classical level in this way. Okay. So now I go to the first transition, rewriting the Newtonian equations of motion in a more flexible formalism. Now there are two motivations for doing this, and I'll give you both of them. The first motivation, I think I have sent to you the typed version of this material once. Did I?
You sent me the constraint dynamic.
Oh no, that's different.
This one you did.
Yeah. I don't know if I should say such things knowing that I'm going to be seen on YouTube. It's a little bit of a constraint. Anyway, let me just say, in December 2011, I was asked to give a set of lectures on classical mechanics at an advanced instructional school on mechanics at the University of Hyderabad. That material is available in print in typed form, and I am essentially following that. So if you give me access to a computer later in the day, I can pass it on to you, and you can print it out, distribute it, whatever, if it is convenient, because then you know you have the text before you. But do come and listen to me Okay, so but you don't have, I can once in a while omit some steps. I can say look at the notes. So we'll do it today. Okay, very good. So there are two important motivations for rewriting the Newtonian equations of motion in a more flexible form. The first motivation is that there may be constraints on the coordinates, on the vector position variables of this system of n particles. So there may be constraints. For example, physically you can easily imagine, if you want to describe the motions of a rigid body, you can think of a rigid body as a collection of mass points with the condition that the distance between any pair of points is always the same. So you don't allow deformations. Okay? So that would be a set of constraints on the Cartesian coordinates of the particles of your system. So it may be example of a rigid body. It could be something else. You might imagine restricting the motion of a given body, given particle, to some surface. For example, the surface of a sphere, or it has to lie on some curve in three-dimensional space, etc. Things of that kind. That is one reason for expressing the equations of motion in a new language. The second one is the following. Suppose in some practical problem you want to use not Cartesian variables but some other variables because the equations become simpler from a practical point of view. In that case, what happens is, see, the brute force method will be, if you do not wish to use Cartesian variables but some other variables because they are mathematically more convenient, the simplest, the direct method would be start with the equations of motion for Cartesian variables, rewrite every one of them with a lot of algebra in terms of any other variables you would like to use. That method of rewriting is always sure to work, but it turns out one can simplify the process of going from Cartesian to any other system of variables. One can simplify it enormously by the Lagrangian method, which is what I am going to describe. Now, the constraints themselves, well, you can read Sommerfeld's book, for example. All these are very well described. There are different kinds of constraints which people define, one for each word in the Greek language. There are constraints which are called holonomic. I won't write it down. You will get the typed version soon. These are conditions involving the coordinates x1 up to xn alone. Then there are constraints which are called non-holonomic. In those, you may have conditions which involve x1, x2 up to xn, as well as the velocities x1 dot, x2 dot, and xn dot. When that happens, usually the assumption is that the velocity dependence is at most linear. Then you might have constraints which are time independent. They have a certain name, rheonomic. You may have, on the other hand, constraints which do depend on time, which keep changing with time. They are called scleronomic. I am just giving a list of different possibilities. As I said, one for each Greek word. Then you may have conditions on coordinates which are written not as equations but as inequalities. You may have a particle limited to a certain region of space and so on. So once you introduce the idea of constraints, you have to say, yeah, they may be of this kind, that kind, so on and so forth. We will look at the simplest possible type, what are called holonomic constraints and time independent. So that's the simplest, and that's the only one we will look at. Conditions which restrict the Cartesian coordinates of the system of particles at each time and nothing more. Okay? No dependence on velocities, no dependence on time. So once again, now this is very well described in the Sommerfeld book. There is an important physical fact, and that is the following. Suppose you have some constraints on the coordinates, Cartesian variables, and you imagine a motion of the system from time t to t plus delta t, always obeying those constraints. Now, whenever there is a constraint acting on these coordinates, in the Cartesian description, in the force on the right hand side, there will be terms which are called constraint forces. Why are they there? They are there so that the constraints will always be satisfied. So that's easy to understand physically. For example, if the constraint was to say you have one particle moving on the surface of a sphere, then the constraint force would be something acting radially, pushing the particle to always stay on the sphere. If it has an intention to move away, you push it back. Okay? Now, there is a physical fact that those forces which arise in order that the constraints are always obeyed, they don't do any work. Now, this is a physical fact. It's not a mathematical statement. It's a physical fact. So this idea of not doing any work means first you have to define what is work. All right. So I go through it in this way. Suppose that, so this is the definition of the work done by a force. This is something you know. I will just write it first and then explain it. Supposing that a force F acts at a location x. The force, every force has a point where it acts. So capital F is acting at the point x. Imagine x moves to x plus delta x. The work done by that force in that small displacement is called is written as delta W. So the physical fact about constraint forces, so I can write this schematically in this way. If there are constraints, then they, in order that they be always obeyed, there will be some terms in the Newtonian equations of motion called constraint forces, which are there in order to make sure that the constraints are always obeyed. And the physical fact is no work is done by these forces. Okay. I want to emphasize this part is a physical fact. Okay. Now, there is a very beautiful discussion of this in the Sommerfeld book. You can see many examples for yourself where you see that this is true. And it is here that Newton's third law plays a very important role. Okay. Okay. So one of the motivations in going from the Newtonian description of motion to the Lagrangian is the following. What can be said about the motion of a physical system in which all reference to these constraint forces is removed, is omitted? What is the maximum set of statements that can be made about the equations of motion in which those forces are completely absent? They are physically there. Their property is that they don't do any work during the actual motion. So can we extract from the large number of Newtonian equations of motion a suitable subset in which the presence of the constraint forces can be ignored? What can be said about the motion without referring to these forces? Now, again I refer you to the Sommerfeld book. There are some important principles which were enunciated in the 18th century. Principle of virtual work, and then a more comprehensive principle called the D'Alembert principle. The principle of virtual work is a statement about a physical system in equilibrium, not moving at all. The D'Alembert's principle is a generalization of the principle of virtual work for the general situation where there is motion. So, I will not go into those principles, but I want you to be aware of them, and as I say, they are very beautifully described in the Sommerfeld book, maybe also in the Goldstein book. Okay. So, now let us see how we make this transition from Newtonian to Lagrangian form of mechanics. So, now there will be a little bit of derivation. Go through it carefully. So, I will write the equations of motion in the Newtonian form, which you can see faintly on the board in a simpler notation. We have n three-dimensional Cartesian vectors, capital N. So, the total number of components is 3 times capital N. So, we will just use a single index j, which will now run from 1 up to 3 and counting all the components of each of these vectors. So, in this notation, sorry, I think I should write it in the, yeah, let me write it in this way. Sorry. The mass will be indexed by this same j going from 1 up to 3n, but it is understood m1, m2 and m3 are all the same. They are the mass of particle number 1. Then m4, m5, m6 are the same, the mass of the second particle, and so on. Then we can write the Newtonian equations of motion in this form, where j goes from 1 up to 3n, and this is the total force, appropriate Cartesian component on the appropriate particle depending on the value of j. Okay. Now, let us write the constraints on these coordinates in the following way. Introduce a notation. Imagine that we have a set of independent restrictions on the Cartesian positions, and how many shall I say? This is a matter of notation. I just list them in this way, the subscript a going from 1 up to the number of Cartesian variables minus something. Okay. Well, in the notes which you will hopefully get sooner or later, these are numbers, these are the equations. So, now we will say that the forces appearing in the Newtonian equations of motion can be split into two parts. x and c. X's are the known forces of a physical origin due to other particles in the system, due to external fields on the whole system, and so on. It is the other part in each force, Cartesian force component F, which I write as a constraint force. The forces which are needed in order that these restrictions be always satisfied. So those are the forces of constraint. This is this part.
So the particles depend on all the x's.
You just allow it. Of course, if you take a system of particles making a rigid body, each phi refers to two of the particles and says that the distance between them should not change. For the case of a rigid body, it would say in the original so we might have a system of equations. So each phi, if this is all, would depend on two of the particles, not on the rest, and so on. And but then you have to write enough of them to make it into a rigid body. And a quick, since you and I asked this nice question, suppose the constraints we have in mind are those corresponding to this system of n, capital N particles forming a rigid body. Then how many independent variables should be left if all the constraints are satisfied? It must reduce from 3 times capital N down to 6, right? What does that mean? The number of constraint independent conditions must be 3n minus 6. Little n would be 6 in the case of a rigid body. Okay, so that is the way in which notation is set up. Okay, so now the physical fact about these constraint forces is the following. I'll write it in this way. Maybe I go to this board, and then you will understand what it is that we have to accomplish. So the equation of motion is written here in the Newtonian form, Cartesian coordinates. The mass times the acceleration of each particle is the total force on that particle, and that total force has a part coming from true physical origins, a part coming from the need to obey the constraints. And so here is the physical fact that the constraint forces do not do any work. I will write it, and then you will understand immediately why it is written in that way. I imagine a motion in which each of the little x's changes by a little amount, always obeying the constraints. Other than that, I allow them to be completely arbitrary, independent of each other. And I put the known forces of physical origin on the left, and I leave the constraint forces on the right. And the physical fact is that the work done by the forces capital C, the total work done by them is 0. So this is not a mathematical statement. This is a physical statement. In all the simple examples you can think, basically in the case of rigid bodies, it is because of being perpendicular. Okay?
But in the case of frictional forces,
Friction is a different matter. I will only look at the case where you have constraints of this kind obeying this principle that they don't do any work. Okay. Friction is a different matter. That I will leave to the statistical physics part of the course. So I want to emphasize this is not a mathematical statement. It's a physical fact that the constraint forces, in many examples which they are given there in the Sommerfeld book, you can convince yourself that this is true. So at some point, Sommerfeld says, we will define a mechanical system to be one in which the constraint forces do not do any work. He takes that attitude. I think that it is important in understanding a subject to make reasonable looking assumptions to make some progress. Get somewhere, get some result with non-trivial content. Then go back, re-examine the assumptions you made. See, can we relax something? You know, if from the very beginning you want to treat the most general situation, you will be stuck. One has to be pragmatic. So in order to understand a subject better and better, make reasonable assumptions, not outrageous assumptions. See how far you can go, then go back and re-examine the assumptions. That's it. After all, we know, I said Newton's third law of motion is his own very important contribution. And he had in mind certain physical systems, certain kinds of forces, and so on. Newton's third law is violated by electromagnetic theory. When magnetic forces are involved, Newton's third law is not obeyed. But that doesn't mean that we should not study the progress of physics for 150 years, giving up Newton's third law. When the time comes to handle forces which don't obey it, you learn then how to handle it. Okay? Yeah.
So is this valid when the system is not in equilibrium?
Yeah. This is during the actual motion of a physical system, obeying the constraints, whatever they may be, at each instant of time. This is valid during the motion. Okay. If there was no motion, if it was a static situation, these accelerations would not be there. So this is for actual motion. So this is the physical fact. Maybe I just put an arrow here to indicate that the statement that the total work done by the constraints during actual motion, that the work done totally is 0, it is not a trivial statement. It is a physical fact, true in many interesting, important examples. And if your library has a copy of the Sommerfeld book on mechanics, if you bring it by today's tutorial session, I'll read out the statement he has made. And if he makes a statement, you should take it seriously. How many of you know how many Nobel Prizes were given to Sommerfeld's students? Just like to know. How many? Who? Yes? Huh? No. Born was equal, contemporary. Heisenberg 1. 2. Anybody else? Huh? 20? No. That's a little overestimate. But I will give you a hint. 2 more. Anybody know? I'll tell you. These are important, you should know. Hans Bethe. Peter Debye. Debye got it in chemistry though. But he was one of Sommerfeld's early students, even before he came to, where is it? He came Munich, before that period, when he was in Hamburg or somewhere. So 4 of Sommerfeld's students got the Nobel Prize. Second important, interesting historical fact, how many times was Sommerfeld nominated for Nobel Prize? Huh? 80. How do you know? You are correct. You read it somewhere. Very good. But it's an interesting fact. None of his Nobel Prize winning students ever nominated him. Einstein and Bohr did not nominate him. But a lot of other people did nominate him, 80 times. So what must have life been like for him? Can you just imagine? Okay. All right. So this is a physical fact, and this is a statement that constraint forces do not do any work, and the condition under which the motion is taking place is that these constraints are always obeyed from instant to instant. So it means that each one of these, which can be written as the functions phi of x are conditions which must remain 0 at every instant of time. So in an infinitesimal motion, the change in every phi should be 0. It starts at 0 and ends at 0. So the delta x's, they are not independent. That's a constraint statement. So this is true. So now you see that this physical fact is true when this condition is satisfied. How do you, so it means that the delta x's here are not all independent. They are restricted by this set of conditions. How do you handle such a system of equations? Mr. Lagrange told you how. The method of Lagrange multipliers has to be used. And when you do that, then you get the following equation. You take each of these constraint equations on the delta x's, multiply it by a corresponding quantity lambda, add them all up, and then Lagrange's machinery tells you, you can then imagine that the delta x's are not limited in any way. That strictly they are constrained, but you can momentarily ignore that fact. So then let me write the equations of motion which you get. By using the method of Lagrange multipliers, you get this set of equations. So in my notations, this is 8, this is 9. These are called Lagrange's equations of the first kind. The number of these equations is exactly the same as in Newton's way of writing it, but you can see now that you have ended up with a formal explicit form for each of the constraint forces. Okay? It is that part coming with the Lagrange multipliers. So the Lagrange equations of the first kind are, if you like, a way of expressing these constraint forces in a somewhat explicit form. The number of equations of motion is not reduced. Now, the fact that this is called Lagrange's equations of the first kind means that there are Lagrange's equations of the second kind. Right? So, what are they? The idea is, what has been achieved by the Lagrange equations of the first kind is to give you some insight into what these constraint forces are. How is it that they depend on the constraints themselves, and so on. Consistent with this principle that they don't do any work. What has happened is that in order to make progress in this direction, a set of Lagrange multipliers has come into the equations of motion. The next stage would be, and remember, the number of equations here is exactly the same, 3 times the number of particles as in the Newtonian description. Now one can ask a more ambitious question. Out of this, can you pull out some consequences, some subset of equations, differential equations, in which the constraint forces are completely absent, in which these Lagrange multipliers are not needed at all. That can be done. That is what will lead to the Lagrange equations of the second kind. And let me now show you how that goes. And you can see that, as I said in the beginning, this whole, so there is, I hope you appreciate, physical ideas, mathematical description, go hand in hand. But you must know which is which. You must be able to distinguish one from the other. Okay. The laws of motion are not part of mathematics. They are part of physics, expressed using the language of mathematics. Sorry to be making these statements, but I think a purely mathematically trained person, a genuine mathematician, by and large, may not appreciate what comes from actual experiment, what comes from experience, and what is mathematics. Mathematics is a language, and as Feynman says, it's a beautiful language which combines precision and the laws of logic, okay, and allows you to see connections. But mathematics on its own cannot reveal facts about the physical universe, about the world. No? So the laws of motion are the result of experiment of Galileo and others, and we use mathematics in any way which is consistent to explore the physics. So now let us see how we develop equations of motion in which these constraint forces are completely absent. In the Lagrange equations of the first kind, they are there, and here is an explicit form for them, and this description is entirely using the Cartesian description of position. So what we do now is the following. Out of the 3n Cartesian position variables, how many are independent given the constraints phi equal to 0? We have numbered it in such a way that we say small n is the number of independent position variables. That's the way we have numbered it. By independent, we mean algebraically independent. So the recipe is the following. Choose a suitable number of independent functions called q of the Cartesian variables, matching the number of independent variables you expect, such that, so this is my equation 10, such that along with the constraint conditions phi equal to 0, all x's are determined. So I will write it in this way. Here is a choice you have to make, a set of independent functions of the x's. We call them q because that must the notation Lagrange introduced, and these are what are called generalized coordinates. Choose them in such a way that these equations of definition plus these equations of constraint together allow you to say you know every x. If you are given the value, numerical value of every q, and if you are told that the x's are limited by these constraint conditions, then you know every x numerically. So all the freedom remaining in the possible choices of the Cartesian variables are captured in the definitions of generalized coordinates. So I will write it in this way. The number of independent q's is little n. The number of constraints is original 3n Cartesian variables minus little n, and the number of original Cartesian variables is 3n. Okay, so this is just to help you with the counting. Right. So here is the idea. This is a mathematical step. It's a beautiful idea of Lagrange.
Small n is number of constraints or number of generalized coordinates?
Small n is the number of generalized coordinates. It's just a matter of notation, what you mean by small n. Therefore, the number of constraints is 3 times capital N minus this small n. It's just a way in which we arrange our symbols. Okay. So, little n is the number of independent generalized coordinates after all the constraints have been satisfied. Therefore, the number of constraints must be 3 times capital N minus little n to agree with our choice of variable little n. What does little n represent? Okay. So, I repeat, recently I had to give a talk to a very mixed audience about the physical basis of quantum physics, and I just want that idea is still in my mind, and I started by making the following statement to them. One of the principles of Galileo was, at the start of modern science, modern physics, measure what can be measured and make measurable what cannot be measured. How many of you have heard this beautiful sentence from Galileo? Apart from the experiments on the leaning tower and the principle of inertia, you have heard this one. It's a beautiful statement. So to this mixed audience, I said, I go back to what Galileo said in the 17th century early. I repeat, measure what can be measured and make measurable what cannot be measured. And so then I said to my audience, this statement conveys the following idea. Every physical system has certain properties, physical properties. Every one of those properties has a numerical value at every instant of time. This was the idea behind Galileo's statement and what led from what came out of his statement. So the whole of classical physics was based on the idea that all physical systems can be described completely in terms of numbers. Every property of any physical system at any instant of time has some value. And then I said, in quantum mechanics, this is not true. In quantum mechanics, for any physical system, the properties of a system are not numbers. This is what I wanted to convey to my audience in a forceful way. They are new mathematical quantities which cannot be thought of as numbers. They are elements of a mathematical object called non-commuting quantities, which is why we have all the problems of understanding quantum mechanics. This is my context. Now I am saying that this is, and then I went on to say that this gave the whole of classical physics a number-based quality. Everything could be described in terms of numbers. And then I quoted, and then there was a, and then I said, it led also to a feeling that everything in nature is mechanical in a suitable sense of the word. And then there is a quotation from Lord Kelvin at the end of the 19th century, one of the last giants of classical physics. He says, to understand anything, any point in physics is to be able to make a mechanical model of it. So, you know, one has to understand how deep this idea was. And then, after quantum mechanics was discovered, Hermann Weyl, who I hope all of you have heard of him, he makes the statement, the continuum of real numbers has retained its prerogative for the expression of measurements in physics. But the greatest achievement of quantum mechanics is to show that the physical properties of a system are elements of a non-commuting algebra. So that's the most beautiful way I've seen it described, that the whole idea of measurement in quantum systems departs from this idea that everything has a value at each time, which idea goes back to Galileo. Okay. So I think this there is a depth in these things. What Galileo said in the early 1700s was very important, because it was to tell the community, people working at that time, we have to be quantitative. We have to be able, he says, I repeat, measure what can be measured and make measurable what cannot be measured. So pushed to its extreme, human emotions should also be measured. And that is now being done, I suppose, in some way in psychology and so on. But the idea was you have to be quantitative. But that's profound statement led over a couple of centuries to this overarching idea. Every physical property of every physical system has a value at each time, whether you measure it or not. It's in its nature to be a number. And then Hermann Weyl says that is where quantum mechanics departs from classical physics. So why do I say all this? Think of it now in this way. Imagine a set of values for every generalized coordinate. And imagine all the constraints being numerically obeyed at each time. These two set of equations, values for the generalized coordinates plus constraints on the x's, determine the values of every x at that time. All freedom you have is in the choice of the values for the q's. Once you choose generalized coordinates, numerically, every Cartesian variable has a definite value, and you are guaranteed by the machinery set up here that the constraints will be obeyed. So you can say these equations tell you the extent to which you can play around with the Cartesian variables while always obeying the constraints. The freedom available to you is the freedom in the choice of the generalized coordinates.
So there may be more than one choice of Q?
Any number of choices, and we come to that later. You can see that, as you say, all that we have said about the choice of the Q's, it doesn't say here is a way to choose the Q's. It says choose it in any way you like, provided the values you assign to the Q's determine the x's completely, given that the constraints are satisfied. Okay? Okay. So I'll end in a few minutes. Let me see. Yeah. I want to avoid bending down as much as possible. Okay. So I will write a few equations which are obvious. The only infinitesimal changes in the x's which can occur in the course of a motion are of this kind. You allow each q to vary as it likes, then the changes in the x's are fixed. Then the velocities, Cartesian velocities, are determined by q dot. What is q dot? A generalized velocity. Q is a generalized coordinate, q dot is a generalized velocity. And here you can say these are independent and the generalized velocities are also independent. Then I hope you can now see, I am sorry I have rubbed out that equation. The part of the equations of motion of Newton in which the constraints do not appear is this. I will write it, and you go back to some of the earlier equations. You have this is the content of the original Newtonian equations of motion, in which the fact that the constraints do not do any work has been used, and used in such a way that the constraint forces completely drop out. Okay. So, this in the tutorial, if it is not clear, you can ask, we can see how this comes. But I just want to make this statement. This is the total information from the Newtonian equations of motion, which you can extract in such a way that there is no presence of the constraint forces. Everything else has to be manipulated out, manufactured out of this. So, how to convince yourself of this, we will see. I will continue from this point tomorrow. I will stop now. What will happen? We will see very nice development. The delta Cartesian variables, delta x's, cannot all be chosen independently. They are constraints. So, this equation is to be true for all choices of delta x of this form, in which the delta q's can be chosen independently. So, what you have to do is put this form for delta x into this, do a lot of machinery, and end up with equations of motion, one for each q. Those will be Lagrange's equations of the second kind, what we always learn as Lagrange's equations. And in advance of saying doing this tomorrow, I just want you to leave with this thought. This whole idea of generalized coordinates and rewriting Newtonian equations of motion from the original form into a more flexible form, the Lagrangian method, the Lagrangian approach to mechanics, as I said, was invented in the late 1700s. To this day, in any physical situation where you talk about fundamental forces of nature and so on, you always ask, what is the Lagrangian for the system? I think it's a little bit amazing. 240 years, still that idea that every physical system, leaving aside friction, every physical system fundamentally, its mechanics, its motion is governed by the choice of a Lagrangian. That will come later. So, I just feel, I don't know what you call it, you get goose pimples, that this idea of Lagrange, that all the motion of a mechanical system can be expressed in terms of one function called the Lagrangian, is apparently such a deep idea, such a deep concept, it is still relevant today. This is all based on non-relativistic physics, as I said in the beginning. It continues to be true for relativistic mechanics. It can handle electromagnetic theory. It even goes into quantum field theory. Every quantum field theory of particular kind. Suppose you ask, what is the, how do you describe the weak interactions of nature? There is a Lagrangian for it. Of course, in the language of quantum mechanics. How do you describe the strong interactions? There is a Lagrangian for it. So, I want you to appreciate how profound this idea of Lagrange has been, that 250 years after he introduced it in a limited context, you must say, it has survived. It remains the way in which physicists always think of any physical system. Of course, in quantum mechanical calculations, in the whole of quantum chemistry, for example, for any system of importance, they say, what's the Hamiltonian? What is the Schrodinger equation? Where does the Hamiltonian come from? It comes from some Lagrangian. So, I just want to convey this importance. So, I think I stop at this point. I keep straying a little bit from the notes, but I think you must know how many Nobel laureates Sommerfeld guided and things of that kind, in addition to lectures on classical mechanics. Okay, it's a good time, right? Stop. Thanks. No, let's keep it for the end. Yeah. Okay.
Was Lagrange motivated by somehow constraints, or
Yeah,
did that you know come out later as a useful?
No. I think it was there from the very beginning. But as I said, there are two motivations one can say. One is if there are constraints, how to handle them, how to obey them. What is left when you remove all reference to constraints? Independent equations which are left. Second, even if there are no constraints, you know today, if you have a spherically symmetric problem in mechanics, instead of x, y, z, it's better to use r theta phi. Should you go back to the differential equations of Newton and laboriously replace Cartesian x, y, z by r theta phi and r dot with or is there a short circuit? That we will see. It is what he discovered. Yeah, sure.
Even if the usual Lagrangian function assumes that you can separate the kinetic and the potential energies, but it happens that in the recent work in the cosmological theory of dark energy, the Lagrangian function is still where when you cannot separate the kinetic and potential.
Yeah, that part is you're right. Yeah.
Even if it is not separable, start interacting Lagrangian, then also it is true.
Yeah, it is true. Thank you. Thanks.
So just a small announcement for registered participants and also for others. Like, if you want to consult books, I mean, some books are kept on reserve in the library, but you can also browse through like other titles. So the library is just one floor up in the same building. So you can go there. The timings are 10 a.m. to 5 p.m. Okay, thanks. Will you remember? Yeah, I'll tell you. So you need it